Hello and welcome. On the bench today I have a server power supply. It's broken, so I'd like to see if I can fix it. It's an Ablecom power supply. I believe it belongs to a supermicro server, and I see the red dot in here. I have a feeling Ablecom and supermicro, maybe they are related, I don't know. But it says here it's a 12-volt power supply, so this is not outputting the usual ATX voltages. I guess there will be like a backplane inside the server, which is then converting those 12 volts into all the relevant voltages that a motherboard, a computer, might require. So this is only outputting 5 volts standby at 4 amps, which is quite a lot for a standby voltage, and 66 amps at 12 volts, which means this is an 800 watts 12 volts power supply. Now these are usually installed in a redundant way, that is, there are more than one in a server, that they can usually be hot swapped, so you just remove one while the other one continues powering on the server, you get an alarm and just plug another one in, and everything goes on, and so you don't have to switch off the server basically. And they come with an edge connector, so it's a bit less straightforward to diagnose, but I believe I found online the pinout of this thing, so it should be more easy than you'd expect. Also, it's just 12 volts, so you don't have lots and lots of voltages, it's just 12 volts and plus 5 volts standby. Not much to see on the other end, it's just 12 volts in, the release lever here, and two very noisy fans which are installed in series, one after the other. Now, as I said, I believe I found a pinout online, so that's a massive help. And some time ago, I made an adapter. I basically used a little edge connector. I think I reused something I had. So this should be kind of plug and play. The red and black cables are the 12 volts. Then I have a convenient switch in here. I got tangled. I have a convenient switch in here for the power on. And these are going to be the plus 5 volts standby, so we can see whether there is any signs of line when you just apply power, because that should come up immediately after power is applied. Now, if I've done my homeworks right, these plugged like this, that's it, and it should work. So hopefully this is going to make my repair attempt a little more straightforward. Finger crossed. So let me thank today's sponsor, PCBWay, and now let's get started on this power supply. Quick disclaimer, working on a power supply is extremely dangerous. There are lethal voltages inside, higher than mains. So if you don't know exactly what you're doing, don't work on power supplies. I don't really know exactly what I'm doing, but I think I'm taking all the necessary precautions. Now, I would say before we even try and power it on and anything, let's take a quick peek inside. Let's see what's inside. Oh, that's simple. Alright, I like how this is constructed. Obviously, this is a server power supply, so it's pretty crowded inside, but probably not too much, though I'll have to take it out of the shell to be able to see something. We got mains coming here, we got a number of filtering sections in here, and this is the main bull capacitor. This is where you're getting about 400 volts, 390 I think, because this will have power factor correction, which I believe happens in this area here. I don't know, I see lots and lots of semiconductors in here. I should be able to understand what happens once this is out, and I can probably shine some light in here and identify which is which. Now, first thing first, I think I'd like to try and power this on, and I think I will clip my multimeter on the legs of the capacitor, which I don't really know. It doesn't say the voltage and the capacitance, everything is at the back, at the bottom actually. I'd like to see whether I'm getting 390-ish volt, because that would tell me a number of things. Number one, it would tell me whether the power factor correction is working. Number two is telling me whether voltage is coming in, because if I don't have voltage there might be a broken fuse, there might be a, I don't know, something else that it means the bridge rectifier is not working, there could be a short. So by plugging my multimeter there, I get quite a lot of information as a starting point. Now I'm going to power these through my current limiter, so I don't really have to worry about these going too bang. I will probably wear some protections. Let me just quickly wire my multimeter, and then we can power it up and see what happens. Alright, I'm wired in, I've got mains coming in, still not powered, and multimeter wired to the capacitor. And I plugged in my little contraption here. This should basically ground the power on pin. Once again, I'm using a current limiter, so nothing terrible should happen, finger crossed. So let's give it a go, 3, 2, 1, go. Yes, 340, so that means the power factor correction is not active. This is just mains being rectified. This is telling me that the fuse is working, the bridge rectifier is working. And let's see what happens if we try and turn it on. I haven't got anything connected to the output though. But first, let's see if the voltage changes, the fan starts, see what happens. 3, 2, 1, go. Nothing. Absolutely nothing. No fan, no change in voltage. I'd imagine we don't have 12 volts as the output. I've removed power because I wanted to wire my other multimeter to the 5 volt standby. Let's turn it back on. 3, 2, 1, go. And we don't have absolutely anything. We don't have 5 volt standby. And I think this is a good clue, because I think the 5 volt standby is a complete different circuit. Doesn't have anything to do with the main switching of the power supply. So it sounds like maybe something's happening before the main switching controller. What we need to do now, we need to discharge this capacitor, of course, and take this out and inspect. To discharge the capacitor, I'm going to use a little oven light bulb. And this is giving you an idea why I'm saying don't touch power supplies unless you know what you're doing. We got the main capacitor discharged, which is slowly going up again. That's totally normal. And now we can hopefully safely remove it from the chassis and take a look, especially underneath, to see if there's anything obvious. Alright, the power supply is out. I had a quick look, and I'd like to show you how the voltage, the power is going through the power supply. Now, mains is coming through here, and at the front there are a number of filtering components for mains, and eventually the voltage is going in that direction. And down here we have our bridge rectifier, which is more or less impossible to show you. It's on this heatsink, and it's definitely a bridge rectifier. So from here, more or less, we have 340 volts DC. Now there is a little vertical board in here, and this IC here, it's a UCC3818AD, and that's a power factor correction. So in this area here, it's where the power factor correction is happening, and that should take the voltage up to about 390 volts. Now, I'd imagine the components for the power factor correction are inside these heatsink, and unfortunately they're sandwiched inside the heatsink, so I can't really see what they are without removing the components and the heatsink at the same time. So let's assume that this area here, where we got the bridge rectifier here, and the power factor correction happening here, controlled by this little vertical board here. Now you can clearly see on this power supply that this is our primary section. Actually, this is our primary section, and everything else is our secondary section. There are always gaps. The gaps are in case there is an arch. If there's an arch because there's an over voltage coming from mains, so something happens here, well, hopefully the gap is enough for the voltage not to jump across the circuit and potentially reaching your computer, reaching the outputs, which is not going to be great. So on the primary section, in this area here, we have the bulk capacitor. So we know that we have 390 volts in here when the power factor correction is working. And the voltage is eventually, let's say, is continuing in this direction here. And it's pretty clear right now that this is our main switching, let's call it transformer, and it's not this one. I don't really know what that is. So if you do know, please leave a comment down below. But this is our main switching transformer. And the component in here is the UC3895DW, which is the main switching controller for the whole power supply. Now there are 6 MOSFETs connected to this heatsink, so I'd imagine these are the main switching MOSFETs, which are getting the voltage not from the capacitor but through the capacitor, and they're being controlled by this little IC here, and they are using this little transformer to generate switched voltage to the secondary section. And on the secondary section, I'd imagine these are diodes. Unfortunately, I'm unable to see the label of those components. It's completely inaccessible. And then we have a couple of inductors in here to smoothen all the signal, and eventually we have the outputs. So this long board in here is our controlling board, where the main controlling IC is located, and also we have the feedback. Obviously, we have 3 trimmers. I don't know what they're doing. I'm not going to touch them. And also, you might be able to see it buried in there. There is an optocoupler, which is the only device which is allowed in between primary and secondary to send some feedback. So the 12 volts is fed back through the power supply controller through the optocoupler. And this is once again to try and avoid any sort of electrical link between primary and secondary, because if something nasty happens, well, those electrical links could be used by high voltages to go to the secondary outputs, which is not good. This one, I don't really know what it is. So once again, if you know, it must be some sort of filtering, I guess. But I have really no idea. Another thing is, here at the end, we have another heatsink, which has a temperature sensor on it, so it must be important. And there are 6 MOSFETs on it. And I don't really understand. We are on the secondary here, so we already have 12 volts, more or less. I don't understand why we have 6 MOSFETs here, and these SMD ones at the end, they're also 6 MOSFETs. I see on the datasheet of the last 6 ones, which are IR5302, these are used for inrush current. These are supposed to be hot plugged, so maybe that's the reason why you need this kind of protection. I don't really know, so if you do know, please do leave a comment down below, because I'm pretty curious. I've never seen this amount of MOSFETs on the secondary section, and then eventually we have a few more capacitors and the outputs, the 12 volts outputs. Now, this power supply features I2C, which is basically a little feature so that the motherboard, actually the backplane of the power supply, and in turn the motherboard somehow, it can talk to the power supply and sense whether there is an over voltage, there is an over temperature, the fan speed, and all the voltages to make sure that nothing is out of the ordinary. And I'd imagine that the section responsible for talking to the power supply is this section here, because there's one chip that says release 1.0, so that means this is some sort of microcontroller. We'll take a look at that in a second. Also, I see that on this little vertical board we have the temperature sensor from this heatsink, then we have the LED that is on at the front, and also the fan. So this is sensing and controlling the fans, the LED, and the temperature sensor, and it makes sense that all those signals can be forwarded to the motherboard as like health status. And indeed, this is a PIC, it's a microcontroller, so obviously this is the little heart of the power supply. I'm actually impressed. I didn't know that I thought these were very dumb power supplies for servers, but no, they actually have a little microcontroller which is monitoring and everything. Now, one thing I haven't mentioned is where the 5 volt standby is coming from. And yesterday when I was looking at this power supply, I thought, I have a feeling that the 5 volt standby missing is the reason why the whole power supply is not working. Now, on a regular power supply where you don't have 5 volt standby, you need some sort of mechanism to generate a little amount of low voltage DC to power on the controlling IC, so the controlling IC can start switching and actually generate the voltage, which will eventually use to power up itself. That's usually done with a resistor and a capacitor, if I remember right. And it's basically a simple mechanism to get a little bit of low voltage from the main rectified voltage, just enough to power on the controlling IC. The controlling IC will start switching and will generate voltage for itself as well. But when you have a standby voltage coming out of your power supply, well, the moment you plug it in, you have a voltage coming out of the power supply. So it makes sense to use that voltage to power on all the electronics on the power supply itself. So if the 5 volt standby circuit is faulty on this power supply, chances are then none of the electronics will work, because probably they all rely on that 5 volt standby. Now, the 5 volt standby can be done in a couple of ways, at least that I'm aware of. One is through a linear transformer. You might have a small linear transformer, because usually 5 volt standby is just like a fraction of an amp. But the lead of this power supply says the 5 volt standby is 4 amps, is 20 watts. It's quite a lot. So I assumed that on this power supply they're using an offline switcher. Now, offline is not like offline online. Offline as in off the line. So it gets mains voltage, rectified main voltage, straight from mains, and that's it. It's got everything inside. It's got the MOSFETs, it's got the controller, it's got everything. So basically you feed mains, well, rectified main to this chip, and you get DC low voltage coming out of it. You might need an inductor or that kind of stuff. I'm not entirely sure. But more or less, it's a small power supply into one chip. And while I was looking where the 5 volt standby was coming from, I found that component there, which is a top. It's a top 244YN, which happens to be an offline switcher IC. And I think I found our problem, because guess what? Well, there's a chunk missing from that IC. And this is not the first time I have a power supply where the top IC exploded. I repaired a power supply some time ago where the top IC went up in smoke in a pretty explosive way. So take a look at that video. There's quite a lot of magic smoke, by the way, in that video. It's quite funny. And I'd imagine, as I said, that if the top is faulty, there's no 5 volt standby, but most importantly, all these components here, which are probably using 5 volt standby to just power up, it would make sense, they're probably not going to work. In fact, on these two boards, I see quite a few of LM393A, which are adjustable 5 volt regulators. So I'd imagine they get whatever voltage is coming out from the top IC, it might be a bit more than 5 volts, and just regulate it down for the power factor correction, for the main switching IC, and whatever is required for the logic and the working of this power supply. So obviously we have a faulty component that we need to address, and I have a feeling that that would be it, unless the top IC, as it happened on the other supply, overvolted on the output and basically destroyed half of the power supply. Well, what I can check is whether we have like a short on the output, but I think what we need to do now is to remove that component and source a replacement. Now, unfortunately, to remove the top IC, I will have to remove the heatsink, and with the heatsink, I'll have to remove 5 MOSFETs. So I'll have to desolder the whole thing, which is probably not a bad thing, so I can make sure that there's no other shorts involved, the MOSFETs are working. So let's remove this whole heatsink with all the components attached. Okay. Before we get into the rest of the video, let's talk about today's sponsor, PCBWay. What I'm holding right here, it's a custom build for a cool project I've got coming in a future video. Getting this manufactured was incredibly simple. I just downloaded a Gerber file, uploaded it straight to their website, and I received the finished PCBs at my door in no time. Here is the almost final result I assembled myself, but PCBWay can also offer turnkey PCBs and install the components for you. I've used PCBWay for countless projects and I'm always happy with the results. I frequently use their custom 3D printing for my hardware enclosures, and they even offer sheet metal fabrication and CNC machining for more industrial builds. A massive thank you to PCBWay for supporting the channels. To bring your own hardware ideas to life, click my affiliate link down below in the description to get started. Now let's go back to the supermicro power supply. And we can see the damage on the top IC. It's, well, there's a chunk missing, so obviously that is, well, at least one of our problems. I don't know if that's the only one. Well, I do know it's not the only one, because now, well, it looks like there is clearly another problem here. I think this component has burnt. Chances are it has something to do with the top. But let me remove the heat shrink and see what's inside. And hopefully we can identify what kind of component that is. And yes, the component has completely exploded. The thing is, I'm not entirely sure what that is. Let me try and clean the PCB, see if, at least if it says, is that like a D, is that an R? Yes. Oh, F. Okay, we are in luck. This is a fuse. That's probably the fuse for the 5 volt standby. I think this is just great construction. I'd imagine that the fuse actually saved most of the components that you see here. Kind of feel optimistic. Touch wood. Well, we are really in luck. I can read 2 amp on the fuse, so I'd imagine it's 2 amps at what, that 390 volts, so that makes sense for a 4 amp 5 volt standby offline switcher. So for now I've got to replace the fuse, I got to replace the top. Now let me spend a little bit of time around the board with my multimeter. I'll see if I can find any further casualties. Now for the MOSFETs I'm going to use my component tester and some wires, and thankfully they're all good. I've got the replacement ICs. Now, before I go ahead and just blindly replace them, there are a few checks that I need to do, otherwise I'm risking that the component will explode again. Now, I was mistaken before. This IC, the TOP244, is not like a whole power supply into an IC. It contains the switching controller and the MOSFET. So you still need, of course, a little transformer, and most importantly, you need a Snubber network. I mentioned that before in a previous video, but in a nutshell, the way a switching mode power supply works is by switching DC, high voltage DC, through a small transformer. This happens at a very high frequency, much higher than mains. Mains is 50 or 60 Hz around the world, and a switching mode power supply is probably around 150,000 Hz. The much higher frequency allows the switching mode power supply to use very small transformers. I mean, to have an 800 watts 12 volts power supply, the transformer, linear transformer, would be massive. So the TOP244 gets 390 volts from the power factor correction and the bridge rectifier, and it switches it on and off through the little transformer. This is done by the MOSFET, which is integrated, it's inside the TOP244. When the MOSFET closes the circuit, well, there is electricity flowing through the little transformer, and when you have electricity flowing through a winding, you generate a magnetic field. The magnetic field is being picked up by the secondary winding in the same transformer, and for a cool effect, when a magnetic field changes, it generates electricity in a winding, and that's why you have electricity in the secondary winding, and then eventually you have lower DC through the power supply. Now, this is very cool, except when the MOSFET opens the circuit. So this is happening, say, 150,000 times a second. Every time the MOSFET opens the circuit, what happens is that you have a magnetic field in the primary winding, and that magnetic field, by definition, because there's no electricity flowing anymore, well, it collapses. And a collapsing magnetic field is still a changing magnetic field, and by definition, it generates a voltage. But the circuit is now open, the MOSFET has opened the circuit, so that collapsing magnetic field is generating voltage which has nowhere to go. And because it has nowhere to go, it basically increases the voltage on that little open circuit itself until it gets to some stupid values. Without any countermeasure, that voltage would go up to, say, 1 kilovolt, and there's nothing rated 1 kilovolt, including the TOP244, which might get damaged by this. So there is something called the Snubber network. It's a number of passive components which are basically there to catch and stop any voltage going over a specific level to basically prevent damage. I found these on the TOP244 datasheet, and it's just an example power supply, 70 watt example power supply, just to give you an idea how things work. This is the top IC, and you can see that you have D and S, that's the drain and the source of the integrated MOSFET inside the TOP244. So 390 volts DC is going through the winding of the transformer, it's going down to the drain, it's being switched on and off by the MOSFET, and then it's going back to the negative of the bridge rectifier. Now, as I said, when the MOSFET opens, you still have a magnetic field in the primary winding. That magnetic field will collapse, will generate a voltage, and we have what's called a Snubber network. In this case, the Snubber network is made of D1, a diode, then we have VR1, that should be a TVS, transient voltage suppressor, and then we have a little capacitor here. The role of these three components is just to catch very, very fast transients over, say, 600 volts and just clamp it down. It basically shorts this voltage to itself. So it doesn't go anywhere, it's very little current. But once again, if you have 1 kilovolt, it's even at very little current, it will destroy components. The very same top IC that we're talking about is rated as a maximum, absolute maximum, 700 volts. So without the Snubber network, well, the component will eventually fail. So I really want to make sure that the Snubber network is working, and I'm looking for a diode, I'm looking for a TVS and a capacitor. Let's take a look. The TOP244 is the U1 IC, that's the footprint, and I can see we have a D1 here is wrapped into heat shrink, and then we have a TVS one, I hope you can see from there, and we have a capacitor, so that's definitely our Snubber network. If we look at the back of the PCB, things are very, very clear. We have the bull capacitor here, this is where 390 volts could be measured, so we don't need to look anywhere else. We have the negative, we have the positive. Now the positive is going here, this is where the fuse was. Now I've removed it, so obviously this is not going anywhere, but eventually 390 volts would go here on these trays here. Now this trace is going inside the transformer and is coming out from here. Now my multimeter is reading 1 ohm. I believe if I put it in resistance mode, well, I have a little bit more accuracy. It's reading 1 ohm. And bear in mind, these probes, I changed the probes, now they're reading 0.1. So we have a little bit of resistance. It's a little winding. So it kind of reads as a short, but it's not exactly that short. And I hope you can see that the trace is going straight into the drain of the top 244. That's exactly what we saw on the datasheet or on the example PCB, the example diagram. So the Snubber network is supposed to be in between the input, the drain of the top, and the main source of 390 volts. And as you can see, this is where the output of the transformer is coming. We have these two components here. I marked them in red. These are the TVS and the diode. So I'm in diode mode now, and I want to read a diode on both of these components. The TVS is a diode. It can be read as a diode. So let's see what we're reading here. That's it. We got 0.464. That's totally fine. And what are we reading on the other one? 0.464. So this is totally fine. We don't have a short. That's what I'm looking for. If the diodes were damaged, they would be shorted or open. They're not open, they're not shorted. And finally, I think here, this part here, yes, we have the capacitor. Again, I'm still in diode mode. I don't care. As long as I don't have a short here, it doesn't read anything. Let's try in capacitance mode. I'm not expecting to read anything, to be honest, but let's see. Yeah, I'm reading a capacitance. That is fine. That is telling me, hopefully, touch wood, that the Snubber network is working totally fine. We don't have a short. So hopefully the reason why the top 244 blew up is not because the Snubber network was not working. And we'll check later on with the oscilloscope to make sure there were no like stupid peaks over 700 volts. But I feel comfortable now in replacing the top, hoping that it just blew up because it decided to blow up. Now, when I looked for the fuse, unfortunately, I couldn't find a very small fuse as the one that was installed in here, and I'm a bit puzzled about that. Now, as I said, we have 390 volts DC in that spot, and we might have some spikes. I would definitely expect something around 500, 550 volts in that spot. And this is the smallest fuse, which is rated 600 volts that I could find. Anything smaller than that, it would be like 125 or maybe 200 volts. And I don't feel comfortable installing a 200 volts fuse where you definitely have 390 volts DC as a minimum. So I'm not entirely sure where that fuse came from. Unfortunately, the case of the fuse only mentioned 2 amps. And I also had to make a decision whether it was 2 amp fast or slow. I went with the slow version. This is going to be a bit chunky, but obviously I'll put some heat shrink around it, and I'm hoping this is not causing trouble. I think I now feel comfortable enough to swap the 244, swap the fuse, give it a go, and cross my fingers. So let's go ahead. Now, just to be on the safe side, let's double check all these small components here. There's some resistors and there's a diode. Just make sure there's nothing fully open, fully shorted. The diode reads as a diode, so that's totally fine. Let's check the resistors. This is reading 4.9. It says 4R75, so I think that is totally fine. This is also 4.9, and this is also 4.9. Now, this is supposed to be 5.1 but kilo ohms, not ohms, but I see there is another resistor here, which I believe is reading the same. Yeah, so I should have tested before. I think I might have done it. 5.3, I'm probably reading something else. I'm probably reading the MOSFETs, I'd imagine. I don't know. That's another 5.3. And that's another 4.9. And this is another 5.3. I mean, I guess as long as they don't read like open or short, I think resistors, they fail open, they don't fail short. I think reading 5.3 is probably nothing to do with a failed resistor, assuming there is one. This is 1 mega ohm, and I believe this is what it says on the top of the case. And also this one is a 1 mega ohm. And this 22 kilo ohms, and it says 2212 on top, so that should be also okay. According to the label, it should be a 7.5 kilo ohms. Well, I'm reading 5. Again, it's in circuit, so that's probably fine. And this one is an 8.1 epsilon, which according to Google is supposed to be 6.8 ohm. I'm reading 26, so that's also probably totally fine. There is a capacitor here. Let's just make sure that it's not shorted. Well, it's not shorted. That's all I'm looking for, to be honest. And there's not much else happening in here. So hopefully this is it. I think I'm ready to put this back into the case and test it. Power supply is plugged to my current limiter isolation transformer. I set the current pretty low, so when I power it up, I'm expecting 5 volts standby on the fluke. And it might struggle a bit at the beginning because it will need to charge this big capacitor, and I don't have enough power right now set on my current limiter to charge the capacitor in one go. So it might hiccup a little bit before it gets to 5 volts, but hopefully we see 5 volts. If we don't see 5 volts, well, then it's not working. Let's turn it up. 3, 2, 1, go. Okay, this is clicking. I turned it off. We do have 5 volts standby. And I think it's trying to start, even though I think I have the switch set to off. Let me switch it to on. I don't have a working power supply like this, so I can't really assume things too much, but it was definitely trying to power the fans. So let me try and switch that to the other position. But we do have 5 volts. I'm really happy with that. 3, 2, 1, go. No. Oh, well, maybe I have the on-off switch in the wrong place. This seems to be trying to start. I would say let's give it a little bit more juice and cross our fingers. 3, 2, 1, go. Okay. Okay, I think this is not started. This is wired to the 12 volts. I mean, this is amazing. It's working. We have 5 volts. And I think this is in standby mode. So this is switched off, but the fan is still running. And why? Because we have an offline switcher inside, which is running and generate heat. So probably the fans is never supposed to stop on this model, at least with this configuration. I know that the server where this is coming from, it will switch completely off, but probably some setting that comes from somewhere. Let's try and switch what I think is the power on button to on. 3, 2, 1, go. Yes! Look! It's working! 12 volts! It's working! I'm super happy. 5.1 volts standby and 12 volts out of the whole power supply. Just fantastic. Now, before we finish the video, I close it up and I test with some load. I think I'd like to try and power this up outside of the case. I want to be 100% sure that the Snubber network is working. For that, I will need my oscilloscope and my differential probe. Differential probes are probes which are not referenced to ground, so allows me to connect the oscilloscope, which is referenced to ground, to anything I want. And so I don't have to worry about voltage going to the wrong place. And the differential probe is wired to the negative of the capacitor and the drain input of the top offline switcher. So I'm expected to see some pulses, and I'm expecting to see a little bit of ringing when the MOSFET opens and the magnetic field collapses, but not too much. I'm not expecting to see 700, 800 volts. That would mean that the Snubber network is not working. 3, 2, 1, go. That's it. Those are our pulses. Let me just reframe the oscilloscope so we can see that better. And this is what I was talking about. So obviously when the MOSFET is closed and the current is flowing, well, the voltage between those 2 points is 0. So my probe is reading 0. When the MOSFET opens, suddenly the voltage goes up, and it goes up to 642 volts, maybe a bit less. Yes, I think I've got the bottom is not very much well aligned. Let's see, let's say 630 is not too far away. And that's when the Snubber network is clamping the voltage, is preventing the voltage to go even higher. Then the voltage stabilizes, eventually the MOSFET will close again, and the current flows, and the voltage red between those 2 points will go down to 0 again. Now, what I wasn't expecting is to see, I would say, this substantial peak at 632 volts. It's still within tolerance, but I was kind of expecting this to be mitigated a bit better, let's put it that way. That being said, I have no idea, I don't really know, that chances are this is totally fine, and this is within the maximum tolerance, so probably is fine. Now, I do have another one of this power supply, which is faulty as well, unfortunately, so I can't just open it up and test it. And I'm planning to fix it as a Patreon exclusive video. So if you're curious, join my Patreon. The link is down below in the description. Once it's working, assuming I can fix it, I will do exactly the same test and I will compare the behavior at the switching. And if it's exactly the same, I guess it's pretty unlikely that we have two power supplies with the Snubber network not working. But so far, I think I can be happy with this. I think I'll consider this fixed. I can put it back into its case, and I think I'll run some load test. I do have a 400 watts load, which I tested in this video at some point. It wasn't a very popular video, so if you're curious. Now, before I start the dummy load, I think I realized what those MOSFETs at the end are. The output of the MOSFET is basically wired to the 12 volts output. So I think those are like, it's a big switch. This is a server grade power supply. If it fails, it can't possibly take down the whole server. So I think this device has the ability to remove power, whatever happens, probably even when you remove the cord, or there's an over voltage or an under voltage or whatever. I believe the first thing that happens is that the output is immediately cut. So the server can continue with the other power supply. And I've realized that I don't have a suitable power connector to extract 400 watts out of this power supply. Also, I have this kind of thin wire, so I think probably 100 watts is the best I can do. So I downgraded to my 8-torch dummy load. It's a bit more camera friendly because it's facing up. I'm now wired straight to mains. 3, 2, 1, go. And obviously starts without any hesitation. We don't have voltage yet, so let's turn this on. 3, 2, 1, go. We have 12 volts, and let's begin with 1 amp. Yeah, we do have 1 amp. 2, 3. And there we go. We got 107 watts. I mean, the wire is not getting warm. I could probably do a bit more, but again, I'm not entirely sure it's a wise thing to do. We have 107 watts, 9 amps as I selected, and obviously the standby voltage is totally fine. I guess I'll keep it running like this for a little while to make sure that nothing nasty happens, it doesn't overheat, nothing horrible happens, and then I'll move to my second one. It's an identical power supply, and as I said, that's gonna be an exclusive Patreon video. I have a few exclusive videos on my Patreon page. They're not too many, so I'm not trying to sell you smoke, but this might be either the third or the fourth one, something like that. There's also a free tier if you want to just join, just to show support. Obviously the free tier, I'm sorry, it doesn't include the exclusive videos, but you know, if you want to take a look, the link is down below in the description. I'm also on Facebook, and if you enjoyed this video, I would really appreciate a thumb up down below, and maybe consider subscribing to this channel and my second channel if you like this kind of things. If Patreon is too much for you, well, maybe you can buy me a coffee, and the link is also down below in the description. If you don't want to support me in any way, that is totally fine, and I really hope that you enjoyed the video. Well, that's it for today. Thank you for watching. I hope to see you again soon here on my channels for my next videos. Thank you very much, and goodbye. Bye-bye.